We just talked about interest rate risk. And, well, interest rate risk then means, the price has something to do with the price of the bonds can either go up or down as a result of changes in the levels of interest rates. And there are two ways we can measure that. And, those two ways, they're called duration and convexity. And in relation to that, then, how can you immunize a portfolio of bonds in such a way that they are immunized for their duration and convexity? So I'm gonna show you that and what that actually means, right? So in regards to this formula, which is the price formula, there is this term called modified duration, where you take the price of the bond, which is P over here, and you differentiate it once with regards to the interest rate. Well, I mean, we put a minus here and we divide it by P, and the reason why we do that is that we don't want to have a dependency on the nominal amount of the bond. We want this change of the price as a function of change in interest rate, because this is what differentiating with regards to interest rates is, right? So if you're differentiating the price function with regards to interest rate, that means how much the price is going to change as a function of change of interest rates. That's what duration is. But then we divide it by P, which is the price itself, in order to make it into percentage change and not the dollar amount change or the nominal change, right? There's also something called dollar duration, so I'm not showing you that. So this is called modified duration because you're dividing by the price. And we, by the way, multiply by minus because I told you about this inverse position, right? So when the interest rates go up, the price goes down. So there's this inverse relation. And for some reason, people in finance, they don't really like to work with negative numbers. So they say, well, this duration, we don't want to think, because there's an inverse relation. So the duration will always actually be a negative number, right? Negative actually showing you that there's an inverse relation between interest rate and prices. But then we just multiply it by -1 because this is for historical reasons, we want to think of duration as a positive number, right? So that's the only reason we multiply by -1. And this is the formula for modified duration. So if you take this function over here, the price function, which we see here, and you differentiate it with regards to interest rate, you will get this formula out. Right. And notice there's also something called Fisher-Weil duration, which is the one I'm going to recommend you to use for your exercises here and for the midterm project. This is essentially, well, this is the same formula as we've got here. The only difference here is that now we are differentiating with regards to a term structure of interest rates which is not flat. So normally in this case we're saying, well, the interest rate doesn't have this index T, so this is not a typo. This is what the definition of modified duration is. And then Fisher-Weil duration is essentially your modified duration. The only difference here is that you have you're differentiating with regards to the whole term structure of interest rates. Right? So that is the formula that will tell you exactly how the interest rate is going to, how the price of a bond is going to change with regards to the changes of interest rates. And if I want to draw that as a function for you, so what you have got here, what we are really interested in is that this is the interest rate, and this is the price of the bond, right? Price of a bond, right? And the function for that, and let's say this is, you've got this level of interest rate, whatever that is. So this is, let's say, the level of interest rate R. And for that, we have a price here. And so what happens if the interest rates, as the interest rates are increasing, the price is falling. And as they are decreasing, the price is going up. And it's not a linear function. This is essentially the price function. So if you depict this price function in such a such a space, then you would get a function which looks something like that, right? So this is the price kind of interest rate relation, right? And in regard to that, if this is the level of interest rate today, then if I want to depict the Fisher-Weil duration, what would that be? This is I'm differentiating this curve, which is the price curve, with regards to interest rate. So what would I get? What is the duration to this curve? And the level of interest rate today is R. So that would be the tangent, exactly. That would be, so I'm essentially getting the tangent to this one, right? Because notice what you put into that formula would be, at the end of the day, would be a number, right? Would be a number which says something about, if the interest rate is going up by 1%, then by how much the price is going to fall, or if it's going to go down by 1%, by how much is going to increase, right? So that's what it says. And obviously, then this is, if I'm drawing the tangent in there, this is an approximation, right? So it doesn't say, it is kind of correct in and around this area R, but as you get further apart, then it's not true anymore, right? But this is essentially what the Fisher-Weil duration says. This is a tangent to the price function at the level of interest rate, which is current today, right? So that's duration. And here comes the first, what we call first order immunization model, which is the first optimization model I'm introducing today, which is essentially built in there to make sure that if you are investing, because at the end of the day, if you're doing risk management with a portfolio of bonds, what you really want is that you want to not to get a stock in any of those two cases. You don't want to get a stock if the interest rate goes down or up. Depending on what the strategies you've put up with bonds, you don't want to be in a place where you are too sensitive to changes of interest rate, right? And this is what this immunization model is going to help you with. So what you have here is that you're saying, all right, I have some liabilities. This is the price of my liabilities today, right? And this is the price of my assets, right? So I want to buy some bonds in such a way that the price of my bonds, the present value of my bonds today has to be the same as my liabilities. Let's say I have liabilities for 1 billion krona, right? I know I have to pay 1 billion krona today in terms of the value of this liabilities today, right? So if I discount all my liabilities, I have a liability cash flow, and I discount it all back and sum it up to what is their present value today, that's, let's say, 1 billion krona. If I were a pension fund, that might be several billion kronas, right? Maybe hundreds of billion kronas, right? That might be my liability. So at any given time, I know as a pension fund or as a bank, I have an idea what my liabilities are. I'll call that PL. And let's say if we decide that I want to pay these liabilities back with a cash flow from bonds. So a good assumption would be that I want to buy enough bonds that at least today they should have the same value as the value of my liabilities, right? So if I had for 3 million or 3 billion krona worth of liabilities, I want to buy for 3 billion kronas worth of bonds today as well. And now comes the question, if I have 3 billion krona worth of liabilities, and I want to buy 3 billion krona worth of assets, so this case over here would come into to mind, right? Because, well, the easiest way kind of to maximize for the short run is that I put all this 3 billion krona in as long as possible in terms of the level of the interest, the horizon for the interest rate, right? 30-year bond if I can get that. But that would be way too sensitive to changes of interest rates, which is why I can't just do that. So if I only had this formula, this is what, and I'm maximizing some function, let's say I'm maximizing my total return of my portfolio. If I were maximizing the return of my portfolio and the only constraint was this one, I will be exactly exposed to that kind of risk, the second kind of risk that I talked about. Now, this equation is then quite important. That says that the duration of my liabilities and the duration of my asset sides, they have to be equal as well. So, and that brings us to this picture. So what it says that for small changes in interest rate, if the interest rates go up, I want both my asset side and my liability sides, the value of that to fall, and also the inverse should be true if interest rates go down. So that's what this formula says. So you have the Fisher-Weil duration here. You multiply it by your the value of your portfolio, and again the Fisher-Weil duration multiplied by the value of your liability side, right? So if and notice here, this is the duration for your liabilities. This is the duration for your assets, right? So let's say if this number is very big in the one end, right, and negative, and then this value is very small, then obviously you're going to get a big hit on your asset side, which is not a good thing, right? So you don't want to, then you don't want, in the case of going in the long-term loan, if the interest rates go up, as was the case here, then you will get a negative impact. The prices of your portfolio will go down, and if the prices of the liabilities would not follow, then you have a problem, which would be the case again if your liabilities were in the short-term ones, right? So that's what this model says, and you want to experiment with that. Does it make sense? Yeah, it was a question. Yeah, so D is essentially just the the duration of, in this case, this is the duration of your liabilities, and this is the duration of your assets. So you can think of your assets and liabilities as two different bonds, and then you can bonds have cash flows, and for that you can go back to the formula of the to this Fisher-Weil duration formula, which is this one, and you will see exactly what this number should be. So you want the number that you would get for the cash flow. This is the cash flow of your your asset side, and then you can do the same thing where you get cash flow from your liability side. In both cases, you find out what is the duration of that, what is the sensitivity of the present values for your liabilities and for your assets in terms of changes in interest rates, and that sensitivity, you want that to be the same. That means the value of your asset side and liability side have to go up and down at the same time in the same direction.
Okay, so you always try that both these have the same value.
Right. So essentially that is in this case, and notice here what the optimization model wants to find out is the x's, right? So because, well, you have different durations. You see this duration has got this I, right? So you have you don't know which bonds to buy, but you want to buy bonds in such a way that your portfolio of bonds, your asset side, has the same duration as your portfolio of your liabilities. So if this one was fixed, so the right-hand side is fixed and given, you know exactly what your liabilities are, but your left-hand side is not given. You have to decide x's in such a way that your portfolio liabilities should be the same as your your portfolio's duration should be the same as your liabilities duration. Right. So that was what we call first-order immunization, and the second-order immunization has got to do with convexity, right? So here I showed you that you have.
Can I just ask, what
sure.
was the f of x we were maximizing?
Oh, okay, what that is, yeah. I mean, this is just a general function, so that's a good question. So what we are just maximizing f of x, and for the exercise you're working with, I've actually made a specific example of what you can put in that function. Okay. So essentially, the idea with that is you can because see you have the equal signs both here and there. So the important part of this immunization model is actually to do immunization matching. But since you're since you have optimizers at your disposal in your service, so you can use the ability also to maximize something, right? So in this case, you can maximize, for example, the return of your portfolio, which would be a good idea, and that's what I'm suggesting you to do. But you could think of some other objective function as well. Right. So let's get back to the idea of duration and now convexity, where I just showed you that duration was the first order approximation to your price function. So that's a straight line. And the problem with that was if the interest rates are moving too much away from the level of interest rates today, then you get a gap in here, right? And this gap at this side might be bigger than this gap from this side, and that there would be, you know, some problems that you would get because of linearity of the first order approximation, but essentially no problem, because we know that again from algebra or from calculus. We know that you just get the second order approximation to a function, and that would be a nonlinear approximation to, in this case, a nonlinear function, right? So what you get in terms of convexity is the second order, which would be a closer fit to this curve. So at the level today, that would be the same, but that would be a closer fit, essentially. So that if you differentiate the price function one more time with regard to interest rates, then you get what we call convexity. And as the name suggests, convexity kind of measures how convex the price curve is, right? So for some bonds, that would be more convex than some other ones, right? You have, and essentially what happens is that the longer term bonds you have, the higher the duration and the higher convexity you would get. So a second order approximation could give you a closer match. And then we look into, so this is essentially then the formula. You differentiate the second time with regards to interest rate, and this is what you need for your work. You have convexity defined in this way. And then we look into the second order immunization model, which is essentially the model we saw before, plus one other constraint that says the convexity of your assets should be greater or equal than the convexity of liability side, right? So it's, again, like here we had, you just multiplied duration by the sum of discounted cash flows, and the same thing on the liability side. Here, you just multiply it by their convexity, right? So this is the convexity of your portfolio has to be greater or equal than convexity of your liabilities. And now the question comes, why don't we ask them to be equal? But why do I say that the convexity of assets has to be greater or equal? So again, this is not a typo. We actually do want the convexity of our assets to be greater than the convexity of our liabilities. And if you look into this graph, does that kind of give you an idea why is it so? Why do we want our assets to have a higher convexity than our liabilities? What does it mean? So first, let's think of it this way. To have a higher convexity, what does it mean? So we can draw this together. So let's say I don't draw the prices first. I just draw two graphs for convexity. And what I'm saying is that if I'm saying that the convexity of my assets has to be greater, so let's say this is the convexity of my assets, and this is the level today. All right? So this is the convexity of assets. Right? And I say, well, I want that to be greater than the convexity of my liabilities. That means I want something like this, right? So this is the convexity of liabilities. So if that was the case, and this is, well, still interest rate, and well, I mean, this would be for prices. So there's of course some function that they're trying to. So this one, let's say. Okay, I don't mix it up. We can do the prices afterwards. But if you're looking only at the convexity, this is essentially what this graph says. Why is it that it's better to have a higher convexity on the asset side than the liability side? Let's say that today they have the same level, right? So this is level of interest rate today. So if the interest rate goes up, what happens with the prices of my assets? They'll be higher than the liability. Right. And what happens if the interest rates go down? Still higher. So exactly. So that when you have the the convexity of assets higher than convexity of liabilities means no matter what happens with the interest rates, my assets would be more worth than my liabilities. That's the effect of that. It's not always easy to get. In many cases, they would be, they would be kind of a smack on top of each other. But if you could essentially get more convexity on your asset side, then you want to go for that, right? If that was a possibility, you want to strive for that, right? Which is not quite the case with your duration, right? Because with the duration, you don't have this nonlinearity, so it would be higher in one side and it would be lower in the other side. So it's actually not a good idea. You don't want to have higher duration on your asset sides. Right. So that was all I had for the second lecture.